the mind-breaking truth about scale. Imagine for a moment that you could shrink yourself down to the size of an atom and sit on a grain of sand. From your atomic perspective, that grain of sand would appear to be a planet-sized world with vast landscapes stretching beyond your horizon. Now, imagine someone tells you that this grain of sand, your entire world, is sitting inside the Empire State Building. Your mind would struggle to comprehend something so impossibly large. This is exactly what you're about to experience, except the grain of sand is our entire Milky Way galaxy containing 400 billion stars, and the Empire State Building is the observable universe. But here's where it gets truly terrifying. What we're calling the Empire State Building might actually be just another grain of sand sitting inside something infinitely larger. Welcome to the most humbling journey you'll ever take. I'm about to show you something that will make you question everything you thought you knew about size, space, and your place in existence. By the end of this story, you'll understand why every astronomer who truly grasps these scales has what we call the cosmic perspective, a profound shift in how they see reality itself. But first, let me ask you something. Right now, as you listen to these words, do you feel big or small? Most people would say they feel pretty normal-sized, not particularly big, not particularly small. You're probably sitting in a room that feels appropriately sized for you, looking at a screen that fits comfortably in your field of vision. Everything around you makes sense in terms of scale. You are the measure of all things in your immediate environment. This feeling is about to be completely shattered. What if I told you that you are simultaneously the most incredibly tiny speck imaginable, and yet also made of components so small that they make you look like a giant? What if I told you that the room you're in right now could fit into our solar system so many times that the number would have more digits than there are atoms in your body? And what if I told you that our entire solar system, including that room and everything you've ever known, could fit into our galaxy so many times that your brain literally cannot process the number? But we're just getting started, because our galaxy, this incomprehensibly vast collection of hundreds of billions of stars, is just one galaxy among trillions in the observable universe. And the observable universe? Well, that might be just a tiny bubble in something so much larger that we don't even have words for it. Here's what's about to happen to your brain. First, you're going to feel a sense of scale that will make you dizzy. Then you're going to feel small, really, really small. Then you might feel scared because humans aren't designed to comprehend infinity. But finally, if you stick with me, you're going to feel something extraordinary. You're going to feel connected to something so magnificent and so vast that it will change how you see every single day of your life. Let me start with a simple question that will begin to break your brain. How long do you think it would take to count all the stars in our galaxy? Not the universe, just our galaxy, the Milky Way. Let's say you could count one star per second, never stopping, never sleeping, never eating, just counting. One star every single second for your entire life. At 1 star per second, you could count about 31.5 million stars in a year. That seems like a lot, right? But our galaxy contains somewhere between 200 billion and 400 billion stars. Let's use the conservative estimate of 200 billion. At 1 star per second, it would take you over 6,000 years to count every star in our galaxy. 6,000 years! The entire recorded history of human civilization is only about 5,000 years old. Now, here's where your brain is going to start hurting. There are an estimated 2 trillion galaxies in the observable universe. 2 trillion galaxies, each containing hundreds of billions of stars. If you wanted to count every star in the observable universe at 1 star per second, it would take you longer than the universe has existed, much longer. The universe is about 13.8 billion years old. Counting every star would take trillions times longer than that. But wait, it gets worse. The observable universe, everything we can possibly see, might be just an infinitesimally small part of the actual universe. Some cosmologists think the true universe could be millions, billions, or even infinitely times larger than what we can observe. Imagine trying to count something infinite. Your brain literally cannot do it, because infinity isn't really a number. It's a concept that breaks mathematics itself. Now let me make this personal. You know how sometimes you lie in bed at night and worry about problems in your life? Your job, your relationships, your health, money, what people think of you. These feel like enormous, overwhelming concerns, right? They feel like the biggest things in the world, because to you, they are your world. But here's what I want you to understand. Every problem you've ever worried about is taking place on a planet that is a tiny speck orbiting a very ordinary star, which is one of hundreds of billions of stars in a galaxy that is one of trillions of galaxies in just the part of the universe we can see, which might itself be essentially nothing compared to the true universe. This isn't meant to make you feel insignificant, quite the opposite. This is meant to show you that you are participating in something so magnificent and so vast and so mysterious that the fact that you exist at all is basically a miracle. The atoms in your body were forged in the hearts of dying stars billions of years ago. You are literally made of stardust, temporarily organized into the pattern that is you, existing for a brief moment in cosmic time, able to think and feel and wonder about your place in this incomprehensible vastness. But I'm getting ahead of myself. We need to build up to these scales gradually, because if I try to jump you straight to the biggest scales, your brain will just shut down. It's like trying to lift 1,000 pounds when you've never lifted weights before. We need to start with something heavy but manageable, then gradually work our way up to the weights that would crush you. So let's start with something you can actually visualize: the Earth. You live on Earth, so you have some intuitive sense of its size. You know that if you got in a car and drove for 12 hours straight, you could cross a pretty big chunk of most countries. You know that flying across an ocean takes many hours. You have a gut feeling for how big Earth is, even if you can't quite picture the whole planet at once. Earth's diameter is about 12,742 kilometers, or about 7,918 miles. If you could somehow drive around the equator in a straight line at highway speeds, let's say 100 kilometers per hour, it would take you about 400 hours, or about 17 days of non-stop driving. That's big, but it's comprehensible. Humans have driven around the world. We've flown around the world in less than 2 days. We have a human-scale understanding of Earth's size. Now, let's take our first step into the incomprehensible. Our sun is about 1.4 million kilometers in diameter. That means you could fit about 109 Earths across the sun's diameter. Think about that for a moment. Remember how big Earth felt? You could line up 109 of them just to span the width of our sun. If Earth feels big to you, the sun should feel impossibly massive. But here's where it gets interesting. In terms of volume, how much space something takes up, you could fit 1.3 million Earths inside our sun. 1.3 million Earths. If you started counting Earths at 1 per second, it would take you 15 days just to count how many Earths could fit inside our sun. And our sun is just an ordinary, medium-sized star. It's not particularly big or small compared to other stars in our galaxy. It's basically the cosmic equivalent of being average height. There are stars in our galaxy that could fit hundreds of our suns inside them. Already, we're starting to lose our grip on scale, aren't we? Earth felt big and familiar. The sun feels almost impossibly large. But we haven't even left our tiny corner of our galaxy yet. We haven't even begun to glimpse the scales we're heading towards. Here's what I want you to try. Tonight, when it's clear,
Go outside and look up at the stars. Pick one star, any star that you can see clearly. That star you're looking at is probably very much like our sun. It's probably a massive ball of nuclear fire, possibly with its own family of planets. The light you're seeing left that star years ago, traveled through the vast emptiness of space, and is now hitting your retina. But here's the thing that should make your knees weak. That star you're looking at is probably closer to us than the vast majority of stars in our galaxy. Most of the stars in our galaxy are so far away that you can't even see them, even though many of them are much brighter than our sun. The night sky, with all those beautiful stars that seem to fill the heavens, shows you only the tiniest fraction of the stars that are actually out there. Our galaxy contains hundreds of billions of stars, but even on the darkest
Beyond the Milky Way, our cosmic neighborhood. Take a deep breath. I know Chapter 1 was a lot to process. You've just had your first real encounter with cosmic scale, and your brain is probably still reeling. That's completely normal. Every astronomer, every cosmologist, every person who studies the universe goes through this same mental adjustment. The difference is, we're not going to stop here. We're going to keep going until we reach the absolute limits of scale that human science has discovered. But before we zoom out to the largest structures in the universe, let me give you a moment to recover by telling you a story. It's a story about discovery, about human curiosity, and about how we learned that our galaxy isn't alone in the universe. It's a story that will help you understand why the next scale jump we're about to make was so shocking when astronomers first discovered it. For most of human history, people thought the Milky Way galaxy was the entire universe. Think about that for a moment. Everything we just discussed in Chapter 1, all those hundreds of billions of stars, all those incomprehensible distances, all that mind-bending scale, our ancestors thought that was everything that existed. And you can understand why. When you look up at the night sky, you see the Milky Way as a faint band of light stretching across the heavens. With the naked eye, it just looks like a glowing cloud. Even with early telescopes, astronomers could see that it was made up of countless stars, but they had no way to measure how far away those stars were, or how the whole structure was organized. For centuries, astronomers noticed other fuzzy patches of light in the sky. They called them nebulae, which just means clouds. Some of these nebulae were clearly clouds of gas and dust within our own galaxy, but others looked different. They looked more organized, more structured. Some even looked like they had spiral arms, similar to what we now know our own galaxy looks like. The big question was, were these spiral nebulae part of our galaxy, or were they something else entirely? This question led to one of the most important debates in the history of astronomy. In 1920, two astronomers named Harlow Shapley and Heber Curtis held a public debate about the nature of these spiral nebulae. Shapley argued that they were part of our galaxy, distant regions of the Milky Way that we were seeing from an odd angle. Curtis argued that they were separate galaxies entirely, island universes as he called them, each containing billions of stars like our own galaxy. The debate couldn't be settled until someone could measure the distance to these mysterious objects. And that's where our story gets really interesting, because the person who solved this puzzle made one of the most mind-blowing discoveries in human history. In 1925, an astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, using what was then the most powerful telescope in the world. Hubble focused this telescope on a spiral nebula called Andromeda and began taking long exposure photographs, carefully studying the images for clues about what this object really was. What Hubble found changed everything. He discovered that he could identify individual stars within the Andromeda Nebula. Not just any stars, but a specific type of star called a Cepheid variable, stars that pulse with a regular rhythm, getting brighter and dimmer in a predictable pattern. And here's the crucial part. Astronomers had already figured out that there's a direct relationship between how fast these stars pulse and how bright they actually are. This meant that by measuring how fast a Cepheid variable was pulsing, Hubble could calculate how bright it should be.
Then, by comparing how bright it should be with how bright it actually appeared from Earth, he could calculate exactly how far away it was. When Hubble did the math, the result was staggering. The Andromeda Nebula wasn't part of our galaxy at all. It was 2.5 million light-years away, far, far outside our galaxy. It was, in fact, another galaxy entirely, containing billions of its own stars. Let me pause here and let that sink in. Hubble had just discovered that the universe was vastly larger than anyone had imagined. Our galaxy, which seemed incomprehensibly huge, was just one galaxy among many. The universe didn't end at the edge of the Milky Way. In fact, it was just getting started. But Hubble didn't stop there. He turned his telescope to other spiral nebulae and made the same measurements. Every single one turned out to be a separate galaxy, each containing billions of stars, each incredibly far away. The universe was full of galaxies. This discovery was so profound that it's hard for us to fully appreciate it today. Imagine thinking you lived in the biggest house in the world, only to discover that your house was just one house in a neighborhood with thousands of other houses, each just as large and magnificent as yours. Except in this case, the scale was infinitely more dramatic. Now, let me bring you back to the present and help you understand what Hubble's discovery means for our journey through cosmic scale. When we talked about the size of our galaxy in Chapter 1, we were dealing with distances of about 100,000 light-years. The Andromeda Galaxy, our nearest major galactic neighbor, is 2.5 million light-years away. That means the distance between our galaxy and the next major galaxy is 25 times larger than the diameter of our entire galaxy. Think about that ratio for a moment. If our galaxy were the size of a dinner plate, the distance to Andromeda would be the length of about 6 cars lined up end to end. But Andromeda isn't just our neighbor, it's our destiny. Here's something that will blow your mind. Andromeda is moving toward us. In about 4.5 billion years, our two galaxies are going to collide and merge into a single, larger galaxy. When this happens, the night sky will look completely different. Andromeda will grow larger and larger in our sky until it dominates the entire heavens, a massive spiral of stars stretching from horizon to horizon. Don't worry, though. This galactic collision won't be destructive in the way you might imagine. Space is so vast and stars are so far apart that when two galaxies merge, the individual stars rarely actually collide. Instead, they just get stirred up and rearranged by gravity into new patterns. If humanity still exists in 4.5 billion years, we'll have front-row seats to the most spectacular cosmic light show imaginable. But let's get back to our journey through scale. Andromeda, our Milky Way, and about 50 other smaller galaxies make up what astronomers call the local group. This is our cosmic neighborhood, a collection of galaxies that are all relatively close to each other and bound together by gravity. The local group stretches about 10 million light-years. Remember, our galaxy is 100,000 light-years across, so our local group is about 100 times larger than our galaxy. If our galaxy were a dinner plate, our local group would be about the size of a large room. Now, here's where things start to get really crazy. Just as our galaxy is part of the local group is part of something much larger called a galaxy cluster. Our cluster is called the Virgo cluster, and it contains over 1,000 galaxies spread across about 15 million light-years. But wait, it gets even more mind-bending. The Virgo cluster itself is part of an even larger structure called a supercluster. Our supercluster is called the Laniake supercluster, which is a Hawaiian word that means immeasurable heaven. Have that for appropriate naming. The Laniake supercluster contains about 100,000 galaxies spread across 520 million light-years. 520 million light-years. Our galaxy, which seemed impossibly large, is just one of 100,000 galaxies in our local supercluster. Let me try to put this in perspective with another analogy, though I warn you that all analogies break down at these scales. If our galaxy were the size of a grain of sand, the Laniake supercluster would be about the size of a large building. But this analogy doesn't really work because we're not just talking about size, we're talking about the number of objects as well. Here's a better way to think about it. If our galaxy were a single person, The Laniake supercluster would be a city with 100,000 people, except each person in this analogy contains hundreds of billions of stars. The numbers become so large that they lose all meaning. But we're still not done. Just as galaxies group together into clusters, clusters group together into superclusters. Superclusters group together into even larger structures. These are the largest structures in the universe, and they have names that sound like they came from science fiction. The cosmic web, the Great Wall, the Boötes void. The cosmic web is the largest scale structure of the universe. If you could somehow zoom out far enough to see the entire observable universe at once, it would look like a vast three-dimensional spiderweb. The strands of this web are made of superclusters like ours, connected by filaments of dark matter and regular matter. Between the strands are enormous empty regions called voids, spaces so vast that they contain almost no galaxies at all. Some of these voids are so large that they beggar belief. The Boötes void, for example, is roughly 330 million light-years across and contains almost no galaxies. It's so large that if we lived in the center of it, we wouldn't have discovered that other galaxies existed until the 1960s rather than the 1920s. Imagine living in a universe that seemed almost completely empty, with just a few scattered points of light in the vast darkness. But here's what really makes your head spin. All of these structures, galaxies, galaxy clusters, superclusters, the cosmic web, all of this represents just the matter that we can see. We call it ordinary matter or baryonic matter, but it makes up only 5% of the universe. About 25% of the universe is made up of something called dark matter. We know it exists because we can see its gravitational effects on the galaxies and galaxy clusters.
The observable universe, the edge of everything we can see. We need to talk about horizons, not the kind you see when you look across a field or an ocean, but cosmic horizons, the fundamental limits of what we can observe in the universe. Because what we're about to discover is that the universe has an edge, but not the kind of edge you might imagine. Imagine you're standing in the middle of a vast, fog-covered plain that stretches infinitely in all directions. You can see clearly for about a mile in every direction, but beyond that, everything disappears into the fog. From your perspective, you exist inside a circle about 2 miles across. That's your visible world. But you know the plain continues beyond what you can see. The fog creates a horizon, a boundary between what you can observe and what exists but remains hidden. This is exactly the situation we find ourselves in when we look at the universe. We exist inside what astronomers call the observable universe, a sphere of space from which light has had time to reach us since the universe began. Beyond this sphere, the universe almost certainly continues, but we can't see it because the light from those distant regions simply hasn't had enough time to travel to us. The observable universe is about 93 billion light-years in diameter. Wait, let me pause right there, because that number probably just confused you. The universe is about 13.8 billion years old, so shouldn't the observable universe be only about 27.6 billion light-years across? If light has been traveling toward us for 13.8 billion years from the most distant objects, shouldn't the farthest we can see be 13.8 billion light-years in any direction? This is one of those places where the universe is stranger than our intuition suggests. The key is that space itself has been expanding during all the time that light has been traveling toward us. When light left the most distant galaxies we can see, those galaxies were much closer to us than they are now. But during the billions of years that their light has been traveling toward us, space has been stretching, carrying those galaxies farther and farther away. So the light we're seeing now from the most distant observable objects left them when they were only about 4 billion light-years away from us, but those objects are now about 46.5 billion light-years away. The sphere of the observable universe has a radius of 46.5 billion light-years, making it 93 billion light-years across. Let me put this number in perspective. We've been building up to this moment throughout our journey, adding scale upon scale, and now we've reached the big one. The observable universe is 93 billion light-years across. Our galaxy is 100,000 light-years across.
That means you could fit 930,000 galaxies the size of ours across the diameter of the observable universe. But remember, it's not just about the diameter, it's about the volume. The observable universe is a sphere, and the volume of a sphere increases as the cube of its radius. Our galaxy is like a thin disk, but if we imagined it as a sphere 100,000 light-years across, you could fit about 800 million billion galaxies the size of ours inside the observable universe. 800 million billion. That's 8 followed by 23 zeros. That's more galaxies than there are grains of sand on all the beaches on Earth, and each of those galaxies could contain hundreds of billions of stars. But here's the thing that makes this even more mind-bending. The observable universe actually contains only about 2 trillion galaxies. Only 2 trillion. That might sound like a lot, but it's incredibly tiny compared to the 800 million billion galaxies that could theoretically fit in that space. This tells us something profound about the universe. It's mostly empty space. The galaxies, for all their immensity, are like tiny islands scattered across an ocean of emptiness. The average distance between galaxies is about 25 times larger than the galaxies themselves. If galaxies were like dinner plates, they would typically be separated by distances the size of football fields. But even calling space empty isn't quite right. Space is filled with dark matter and dark energy, with quantum fields and virtual particles popping in and out of existence, with radiation left over from the Big Bang, with cosmic rays and magnetic fields and gravitational waves. Space is empty of the matter we're familiar with, but it's far from being nothing. Now, let me tell you about the most distant thing we can see in the universe, because this is where our story gets truly cosmic. The farthest we can see in any direction is not to a galaxy or a star, but to the cosmic microwave background radiation, the afterglow of the Big Bang itself. Here's what happened. For the first 380,000 years after the Big Bang, the universe was so hot and dense that it was opaque to light. Electrons and protons couldn't combine to form atoms because there was too much energy around. Light couldn't travel very far before it bumped into a free electron and scattered in a different direction. The universe was like a thick fog. But then, about 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into hydrogen atoms for the first time in its history. This event is called recombination, and it made the universe transparent to light for the first time in its history. The light that was released during recombination has been traveling through space ever since, and we can still see it today as the cosmic microwave background radiation. This radiation comes to us from every direction in the sky, and it represents the most distant thing we can possibly observe, the edge of the observable universe. When we look at the cosmic microwave background, we're seeing the universe as it was only 380,000 years after the Big Bang. We're looking back in time almost to the very beginning of everything. The light that we're seeing has been traveling for 13.8 billion years to reach us. But here's something that will make your brain hurt. The place where this light originated is now about 46.5 billion light-years away from us because of the expansion of space. So we're seeing the afterglow of the Big Bang from regions of space that are now at the very edge of our observable universe. This creates a strange situation. We can see the cosmic microwave background, we can observe the universe as it was 380,000 years after the Big Bang, but we can't see what those same regions of space look like today. The light from what those regions look like now won't reach us for billions and billions of years, if ever. It's like looking at a photograph of someone taken when they were a baby, but having no way to see what they look like now as an adult. We can see the baby universe, but we can't see the adult universe in those most distant regions. Now let me blow your mind with some numbers. The observable universe contains about 2 trillion galaxies. Each galaxy contains on average about 100 billion stars. That means there are 200 billion trillion stars in the observable universe. That's a 2 followed by 23 zeros. But stars aren't the only thing in the universe. Many stars have planets. Based on what we've discovered with telescopes like Kepler and TESS, it appears that most stars have at least one planet, and many have multiple planets. Conservative estimates suggest there might be at least 100 billion trillion planets in the observable universe. And how many of those planets might have life? We have no idea. Earth is the only planet we know of that has life, so our sample size is exactly 1. But even if only 1 trillion planet has life, that would still mean there are 100 billion planets with life in the observable universe. Of course, most of that life would probably be simple, bacteria, algae, maybe some more complex organisms. But what about intelligent life? What about civilizations? Again, we don't know, but the numbers are so large that it seems almost impossible that we're alone. Think about that for a moment. You exist in a universe that contains hundreds of billions of trillions of stars, possibly hundreds of billions of planets with life, and potentially millions or billions of intelligent civilizations. And this is just in the part of the universe we can see. But now we come to the really mind-bending part. Everything we've discussed so far, our galaxy, our local group, our supercluster, the cosmic web, the 2 trillion galaxies, the 200 billion trillion stars, the potential for countless forms of life, all of this exists within the observable universe. This is just what we can see. The actual universe, the total universe, could be much, much larger. And when I say much larger, I mean unimaginably, incomprehensibly larger. Some models suggest that the total universe could be at least 250 times larger than the observable universe in each direction. If that's true, then the total universe would contain about 15 million times more volume than the observable universe. Instead of 2 trillion galaxies, there would be about 30,000 trillion galaxies. But other models suggest the universe could be much larger than that. Some suggest it could be millions of times larger than the observable universe. Others suggest it could be infinite. Let's think about what infinite means for a moment, because infinity is a concept that breaks our brains in interesting ways. If the universe is truly infinite, then it contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if there are infinite number of planets, then even if the probability of life is incredibly small, there would still be an infinite number of planets with life. But infinity gets even stranger than that. If the universe is infinite and matter is distributed roughly evenly throughout it, then everything that could possibly happen would happen somewhere. There would be infinite worlds exactly like Earth. There would be infinite copies of you living lives exactly identical to the one you're living right now. There would also be infinite copies of you living slightly different lives, versions where you made different choices, where history unfolded differently. This isn't science fiction. This is a serious consequence of what mathematicians call the infinite monkey theorem.
The birth of infinity. How something smaller than an atom became everything. I need you to imagine something impossible. I need you to imagine taking everything we've discussed, our galaxy with its 400 billion stars, the trillions of other galaxies, the cosmic web, the entire observable universe with its 93 billion light-year diameter, and compressing it all into a point smaller than a proton. Actually, let me be more precise about this, because the true story is even stranger than that. I need you to imagine all of space itself, possibly infinite space, compressed into something so small that calling it tiny would be a massive overstatement. We're talking about something smaller than the smallest thing you can imagine, and then smaller than that, and then infinitely smaller still. This is where our universe began. Not just the stuff in the universe, the matter and energy, but space itself and time itself, all compressed into what physicists call a singularity, a point of infinite density and infinite temperature where all the laws of physics as we understand them break down completely. And then, in a moment that defies all human intuition, this infinitely small point began to expand. This is the story of the Big Bang. But I need to warn you right away that almost everything you think you know about the Big Bang is probably wrong. The Big Bang wasn't an explosion in space. It was an explosion of space. It wasn't a bomb going off in empty space, sending matter and energy flying outward. It was space itself coming into existence and expanding, carrying matter and energy along with it.
But even more mind-bending than that is what happened in the first fraction of a second after the Big Bang began. In a period of time so short that it's measured in units with names like Planck time and inflationary epoch, the universe underwent a period of expansion so rapid that it makes everything we've discussed about cosmic scale seem slow and gentle by comparison. This period is called cosmic inflation, and it's the reason that the universe is as large as it is today. During inflation, space expanded faster than the speed of light. I know that sounds like it violates Einstein's rule that nothing can travel faster than light, but it doesn't. Matter and energy can't travel through space faster than light, but space itself can expand as fast as it wants to. There's no speed limit on the expansion of space. How fast did space expand during inflation? Hold on to something, because this number is going to break your brain. In about 10 to the minus 36th seconds, that's a decimal point followed by 35 zeros and then a 1, the universe expanded by a factor of at least 10 to the 26th. That means every distance in the universe got at least 100 billion times larger. To put this in perspective, if you inflated a grain of sand by the same factor, it would become larger than our solar system. But the universe didn't start as large as a grain of sand. It started much, much smaller, and it expanded much, much more than the minimum required by our theories. Here's what this means for the scale of the universe. Remember how we talked about the observable universe being 93 billion light-years across? Before inflation, the region of space that would become our entire observable universe was smaller than a proton, much smaller, possibly smaller than the Planck length, which is the smallest distance that has any meaning in physics. The Planck length is about 10 to the minus 35 meters. That's a decimal point followed by 34 zeros and then a 16. To give you some sense of how small this is, a proton is to the Planck length as you are to the entire solar system. The Planck length is so small that it makes atoms look huge, and our entire observable universe with all its trillions of galaxies and all its mind-bending scale started out smaller than this, possibly much smaller. But inflation explains something else that's crucial to our story about scale. Remember how we talked about the possibility that the total universe might be much larger than the observable universe, or might even be infinite? Inflation is why. During the inflationary period, different regions of the early universe expanded at slightly different rates and at slightly different times. Some regions stopped inflating and began the more gradual expansion we see today, while other regions might have continued inflating for longer periods. This is why our region of space stopped inflating about 13.8 billion years ago and began the slower expansion that created the universe we see today, while other regions might have continued inflating and grown to enormous sizes. Still, other regions might be inflating even now, creating pocket universes of unimaginable size. This is called eternal inflation, and it suggests that our observable universe is just one tiny bubble in what physicists call the multiverse, a vast foam of pocket universes, each potentially infinite in size, each potentially containing its own galaxies, stars, and planets. Think about what this means. If eternal inflation is correct, if the multiverse exists, then every possible size of universe exists somewhere. There are universes much smaller than ours where galaxies never had a chance to form. There are universes much larger than ours where the cosmic web stretches across distances that make our observable universe look tiny. And in some of those universes, there might be beings contemplating their own cosmic scale, wondering about their place in existence, just as you are right now. Some of them might live in universes so small that they think their single galaxy is all that exists. Others might live in universes so large that they've discovered millions times more galaxies than we have. But all of them, no matter what scale of universe they inhabit, would be asking the same questions you are asking right now. How big is my universe? What is my place in it? Am I alone? What does it all mean? These questions connect you to every possible observer in every possible universe. The quest to understand cosmic scale isn't just human, it's universal. It's what consciousness does when it becomes aware of its place in the cosmic order. In our next chapter, we're going to explore what all of this means for the future. We're going to talk about how the universe is changing over time, how its scale will continue to evolve, and what the ultimate fate of everything might be. We're going to journey to the far future and discover that the story of cosmic scale is still being written.
The future of forever, where infinite expansion leads. Close your eyes for a moment and imagine stepping into a time machine. Not one that takes you back to see dinosaurs or ancient civilizations, but one that propels you forward, far into the future. I'm going to take you on a journey through deep time, showing you how the cosmic scale we've been exploring will evolve over the coming billions, trillions, and eventually unimaginable years. What you're about to discover is that the story of cosmic scale doesn't end with our current universe. In fact, we're living during what future civilizations might consider the brief golden age of cosmic scale, a time when the universe is young enough that galaxies are still forming and bright, but old enough that complex structures like stars and planets and life can exist. The future holds changes so profound that they will make everything we've discussed seem quaint by comparison. The universe is not static. It's not just expanding, it's evolving, changing in ways that will fundamentally alter the meaning of cosmic scale itself. Let me start with something that's happening right now as you listen to these words. The universe is expanding, not just getting bigger, but accelerating in its expansion. Every second, the space between distant galaxies grows larger. Every moment, the cosmic scale becomes more cosmic. This expansion is driven by something we call dark energy, the mysterious force that makes up about 70% of the universe. We don't fully understand what dark energy is, but we can measure its effects very precisely. It's pushing space apart, making the universe expand faster and faster over time. What does this mean for the cosmic scale we've been exploring? It means that the distance between our galaxy and other galaxies is constantly increasing. Right now, the nearest major galaxy, Andromeda, is about 2.5 million light-years away. But space is expanding, so that distance is growing. In 1 billion years, if nothing else changed, Andromeda would be slightly farther away due to the expansion of space alone. But something else is going to happen first. Remember how I mentioned that Andromeda is actually moving toward us? In about 4.5 billion years, our galaxy and Andromeda are going to collide and merge. When this happens, we'll become part of a larger galaxy that astronomers have already nicknamed Milkomeda. This galactic merger will be spectacular. The collision will trigger massive waves of star formation as gas clouds in both galaxies are compressed and heated. New stars will be born at a rate hundreds of times faster than they are being born today. The night sky will be filled with brilliant young stars and colorful nebulae. If humanity still exists, they'll witness the greatest fireworks show in cosmic history. But Milkomeda will be just the beginning. Our local group of galaxies, including our galaxy, Andromeda, and about 50 smaller galaxies, are bound together by gravity. Over the next several billion years, all of these galaxies will gradually merge into a single, massive elliptical galaxy. While this is happening in our local neighborhood, the expansion of the universe will be pushing everything else farther and farther away. The other galaxy groups and galaxy clusters will become increasingly distant and increasingly redshifted, their light stretched to longer and longer wavelengths by the expansion of space. This brings us to one of the most profound changes that will occur in cosmic scale. The galaxies beyond our local group will eventually disappear from view entirely. Here's why. As the universe expands, distant objects are carried away from us faster and faster. Currently, the most distant galaxies we can see are moving away from us at about 95% the speed of light due to the expansion of space. But as dark energy continues to accelerate the expansion, more and more galaxies will cross what astronomers call the cosmic event horizon. Once a galaxy crosses the cosmic event horizon, it's moving away from us faster than the speed of light due to the expansion of space.
Light that it emits after crossing this boundary will never reach us. It will be carried away by the expansion before it can bridge the gap between us. This means that sometime in the far future, probably in about 100 billion years, observers in our merged local group galaxy will look out into space and see nothing. No distant galaxies, no cosmic web, no evidence that the universe contains anything other than their own galaxy. Think about what this means for cosmic scale. Future astronomers living in a universe 100 billion years from now will inhabit a single, isolated galaxy surrounded by empty space. To them, their galaxy will be the entire visible universe. They'll have no evidence that other galaxies ever existed. If they develop cosmology, they might conclude that their galaxy is all there is. They might develop theories about how their galaxy formed in empty space. They would have no way to know about the Big Bang, about cosmic expansion, about the billions of other galaxies that exist but are too far away to see. This is a sobering thought. It means that we're living in a special time in cosmic history, perhaps the only time when it's possible to see the universe as it truly is, filled with galaxies and large-scale structure. Future civilizations will envy you. You exist during the brief period when the universe is filled with galaxies and stars and planets and life. You exist when it's possible to see the cosmic web, to study the Big Bang, to understand the true scale of reality. But even this isn't the end of the story of cosmic scale. Let's go further into the future, much further. In about 1 trillion years, something else will start to happen. The stars will run out of fuel. Stars are powered by nuclear fusion, converting hydrogen into heavier elements and releasing energy in the process. But there's only a finite amount of hydrogen in the universe, and stars are gradually converting it all into heavier elements. The most massive stars burn through their fuel quickly and die young, often in spectacular supernova explosions. But even the smaller stars, like our Sun, eventually exhaust their nuclear fuel. Our Sun will die in about 5 billion years, first expanding into a red giant and then collapsing into a white dwarf. Over 1 trillion years, all the stars in all the galaxies will gradually burn out. The universe will enter what astronomers call the degenerate era, a time when the primary sources of light are white dwarfs, neutron stars, and black holes, rather than the normal fusion-powered stars we see today. In the degenerate era, the cosmic scale will still be meaningful because galaxies and galaxy clusters will still exist, held together by gravity. But the universe will be a much darker, colder place. Instead of the brilliant spiral galaxies filled with bright young stars that we see today, there will be dim elliptical galaxies filled primarily with stellar corpses. But we can go further into the future, much further. In about 10 to the 14 years, that's 100 trillion years, even the longest-lived red dwarf stars will burn out. The universe will enter the black hole era, when the only remaining sources of energy are black holes slowly evaporating through Hawking radiation. By this time, the expansion of the universe will have stretched space so much that even our local merged galaxy might start to come apart. The cosmic scale will have grown so large that gravity can no longer hold galaxy-sized structures together against the expansion. Individual stars and stellar remnants will drift apart, leaving behind a universe filled with isolated white dwarfs, neutron stars, and black holes, separated by distances that make the current distances between galaxies seem tiny. But even this isn't the end. We can go much, much further into the future. Stephen Hawking discovered that black holes aren't truly black. They emit radiation and gradually evaporate. The larger the black hole, the longer it takes to evaporate, but eventually, even the most massive black holes will evaporate completely. The supermassive black holes that sit at the centers of galaxies contain millions or billions of times the mass of our Sun. These giants will take an unimaginably long time to evaporate completely. We're talking about 10 to the 100 years, a 1 followed by 100 zeros.
To put this number in perspective, this is vastly longer than the current age of the universe. If the current age of the universe was 1 second, then 10 to the 100 years would be longer than 10 to the 80 current ages of the universe. It's a number so large that it defies human comprehension even more than the spatial scales we've been discussing. But eventually, even these supermassive black holes will evaporate completely. When the last black hole disappears, the universe will enter what physicists call the heat death era. This will be a universe filled only with elementary particles, electrons, positrons, neutrinos, photons, separated by distances so vast that they almost never interact. At this point, the concept of cosmic scale will have lost most of its meaning. There will be no galaxies, no stars, no planets, no complex structures of any kind, just isolated particles drifting through space that has expanded to unimaginable proportions. But even this might not be the end. Some theories suggest that even in the heat death era, quantum fluctuations might occasionally create new structures. In the vast expanses of deep time, random quantum events might.
What it means to be you in a universe this big. We've traveled together through the grandest scales imaginable. We've journeyed from our galaxy to the observable universe, from the Big Bang to the heat death of everything, from the quantum realm to infinity itself. Now we come to the most important question of all. What does any of this mean for you? Right now, as you absorb these words, you are a pattern of matter and energy that has become conscious enough to contemplate the very cosmos from which you emerged. You are the universe thinking about itself. And in a cosmos this vast, this ancient, this complex, your existence is so improbable that it borders on the miraculous. Let me start with a number that will put your existence in cosmic perspective. The atoms in your body had to come together in exactly the right way, at exactly the right time, in exactly the right place for you to exist. The probability of this happening by chance is so small that mathematicians don't have adequate notation for it. But it's not just about the atoms in your body coming together correctly. For you to exist, the universe itself had to unfold in exactly the right way. The Big Bang had to happen with precisely the right amount of energy, just enough to create matter, but not so much that everything collapsed back into a black hole immediately. The laws of physics had to be calibrated with extraordinary precision. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars and planets would never form at all. The first stars had to live and die to create the heavy elements your body requires. Your solar system had to form in just the right location in the galaxy, not too close to the center where radiation would be lethal, not too far out where heavy elements would be too rare. Earth had to be exactly the right distance from the sun, had to have exactly the right mass to retain an atmosphere, had to have a moon to stabilize its rotation. And then, over billions of years, life had to evolve from the simplest molecules to the incredible complexity that is you. Every one of your ancestors, stretching back through millions of generations to the first living cells, had to survive long enough to reproduce. Every single one. The chain of events that led to your existence is so improbable that if you tried to recreate it deliberately, you couldn't do it. And yet, here you are. But your existence becomes even more remarkable when you consider it in the context of cosmic scale. In a universe containing trillions of galaxies, each with hundreds of billions of stars, the probability that consciousness would emerge somewhere was perhaps inevitable, but the probability that it would emerge as you, with your particular thoughts and experiences and perspective, is essentially zero. And yet, here you are, conscious and curious, able to contemplate infinity itself. This leads us to what I consider the most profound implication of cosmic scale. You are not an accident.
You're not a random collection of atoms that happened to stumble into consciousness. You are the universe's way of understanding itself. Think about it this way. For nearly 14 billion years, the universe existed without any consciousness to observe it. Galaxies formed and evolved, stars were born and died, planets condensed from cosmic dust, but there was no awareness, no consciousness, no observer to appreciate any of it. Then, at least once that we know of, on a small planet orbiting an ordinary star in an unremarkable galaxy, the universe developed consciousness. Matter organized itself in such a way that it became aware of itself and its surroundings. The universe opened its eyes and began to wonder about its own nature. You are part of that awakening. You are one of the ways the universe has developed to study itself, to appreciate its own beauty and complexity, to ask questions about its origin and fate and meaning. This perspective, sometimes called the cosmic perspective, changes everything about how you might think about your life and your place in existence. It means that your consciousness is not separate from the cosmos, it's part of the cosmos. You're not looking at the universe from the outside, you are the universe looking at itself from the inside. Every time you feel wonder at a sunset, you are the universe appreciating its own beauty. Every time you feel curious about how things work, you are the universe investigating itself. Every time you feel compassion for another person, you are the universe caring for itself. But the cosmic perspective also provides a powerful antidote to the problems and anxieties that can dominate daily life. When you understand the true scale of the cosmos, when you really grasp that you're made of stellar material and that your existence is part of a cosmic story 14 billion years in the making, it becomes much harder to get overwhelmed by small setbacks. This doesn't mean your problems aren't real or don't matter. Your experiences, your relationships, your joys and sorrows, these are the most real things in the universe to you, and they should be. But understanding cosmic scale provides what psychologists call perspective taking on a cosmic level. You're worried about what people think of you? You exist on a planet that is a tiny speck in a galaxy of 400 billion stars, which is one of trillions of galaxies in just the observable universe. The people whose opinions you worry are collections of stardust, temporarily organized into human form, living for a cosmic instant on this tiny world. This doesn't make their opinions meaningless. The connections between conscious beings are among the most precious things in the universe, but it does put social anxiety in a cosmic context that can be liberating. You're stressed about your career, your finances, your status. You're participating in a brief economic system on a small planet during a tiny window of cosmic time. The money and status you worry about are human constructions that have existed for only the last few thousand years of a 14 billion year cosmic story. Again, this doesn't make these concerns irrelevant to your life, but it can help you see them as part of a much larger tapestry, not as the ultimate determinants of your worth or meaning. You're afraid of death? You are made of atoms that were forged in the hearts of dying stars billions of years ago. Those atoms existed long before you were born, and they will continue to exist long after your current pattern dissolves. In a very real sense, you are immortal, not as this particular arrangement of matter, but as part of the eternal cosmic story. Your atoms will become part of other patterns, other forms of organization. Some will become part of new stars, some will drift through space for trillions of years, some might even become part of new forms of life in the far future. You are not separate from the universe. You are a temporary expression of it. But there's something even more profound than atomic immortality. If consciousness can emerge once from the cosmic process, as it has in you, then it can emerge again. The pattern that is your consciousness, your particular way of experiencing and understanding reality, is part of the universe's repertoire of possibilities. In the vast expanses of cosmic time and space, with infinite opportunities for matter and energy to organize themselves, the pattern that is you will emerge again. Maybe not exactly identical, but close enough that it would be recognizably you. You are not just a one-time cosmic accident. You are a recurring theme in the universe's eternal symphony. Now let me address what might be the most difficult aspect of the cosmic perspective, the sense of insignificance. Throughout our journey together, we've repeatedly emphasized how small you are compared to galaxies, how brief your lifetime is compared to cosmic timescales, how your entire planet is just a speck in an incomprehensibly vast universe. This can lead to what philosophers call cosmic vertigo, a feeling that you don't matter, that your life is meaningless in the face of such immensity. If you've felt this during our journey together, you're not alone. Many people, when first confronted with cosmic scale, experience a sense of existential crisis. But I want to suggest a radically different way of thinking about this. Instead of seeing cosmic scale as diminishing your importance, see it as amplifying your significance. In a universe this vast, consciousness is incredibly rare. As far as we know, most of the cosmos consists of empty space, dark matter, and simple hydrogen and helium. Complex chemistry is rare. Life is rarer still. Consciousness, the ability to think, feel, wonder, and appreciate beauty, is so rare that we've found only one example of it so far, here on Earth. This makes you not insignificant, but extraordinarily precious. You are one of the rarest things in the universe, a conscious observer capable of understanding and appreciating the cosmic story. Think about it this way. In all those trillions of galaxies, with all their hundreds of billions of stars, consciousness might be so rare that you are one of only a handful of beings in the observable universe capable of contemplating these.
The invisible universe, dark matter, dark energy, and hidden dimensions. Everything I've told you so far about cosmic scale has been a lie. Well, not exactly a lie, but a profound understatement of the true scope of reality. Because everything we've discussed, every galaxy, every star, every planet, every atom in your body, represents only about 5% of what actually exists in the universe. The remaining 95% is invisible to us, detectable only through its gravitational effects and its influence on the expansion of space itself. We call it dark matter and dark energy, and understanding these invisible components completely changes the meaning of cosmic scale. Let me start with a thought experiment that will shatter your perception of reality. Imagine you've been living your entire life in a house, completely unaware that this house is actually floating in the middle of a vast, invisible ocean. You can see the furniture, the walls, the windows, everything that makes up your familiar world. But you have no idea that all of this visible matter is just a tiny fraction of what's really there. This is exactly our situation in the universe. Everything we can see, every galaxy blazing with billions of stars, every nebula glowing with cosmic fire, every planet and moon and asteroid, is just the small visible component floating in a vast sea of invisible matter and energy. Dark matter makes up about 25% of the universe. This isn't matter that's simply hard to see, like a black hole or a distant brown dwarf. This is matter that doesn't interact with light at all. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. It's completely transparent to electromagnetic radiation of all kinds. And yet we know it's there because we can see its gravitational effects everywhere we look. When we observe how fast stars orbit around the centers of galaxies, they're moving much too fast for the visible matter alone to hold them in orbit. There must be much more mass present, invisible mass that we can only detect through its gravity. When we look at galaxy clusters, those vast collections of hundreds or thousands of galaxies, we see the same thing. The galaxies are moving too fast to be held together by just the gravity of the visible matter. There must be about 5 times more invisible matter than visible matter to explain what we observe.
But here's where it gets truly mind-bending. This dark matter isn't just sitting passively in space. It forms enormous structures, a cosmic web of dark matter filaments stretching across the universe, with regular matter falling into the gravitational wells created by this invisible scaffolding. If you could somehow see dark matter, the universe would look completely different. Instead of mostly empty space punctuated by bright galaxies, you would see a vast three-dimensional web of dark matter filaments, with the galaxies we can see forming like dewdrops along the strands of a cosmic spiderweb. The cosmic web we discussed earlier, those filaments of galaxies stretching across hundreds of millions of light years, is actually just the visible part of a much larger dark matter web. The scale of the universe isn't just bigger than we thought because of all the galaxies we can see. It's bigger because all those galaxies are just markers highlighting the edges of invisible structures that dwarf them in scale. Think about what this means for your place in the cosmic hierarchy. You exist on a planet orbiting a star in a galaxy that it itself is just a tiny visible marker indicating the presence of a much larger invisible dark matter halo. Your galaxy isn't just floating in space, it's embedded in a vast dark matter structure that extends far beyond the visible galaxy itself. Our Milky Way galaxy sits inside a dark matter halo that's probably about 10 times larger than the visible galaxy and contains about 10 times more mass than all the stars we can see. So when we talk about the scale of our galaxy, we're actually talking about just the bright, visible core of something much, much larger. But dark matter isn't only the story. The other invisible component is even stranger, dark energy, which makes up about 70% of the universe. If dark matter is like an invisible ocean that regular matter floats in, then dark energy is like a force that's stretching the ocean itself, making it grow larger and larger over time. Dark energy is what's driving the accelerating expansion of the universe. Here's what makes dark energy so bizarre. It appears to be a property of space itself. The more space there is, the more dark energy there is. As the universe expands and creates more space, it creates more dark energy, which causes the expansion to accelerate even faster, which creates even more space, which creates even more dark energy. This means that dark energy density remains constant even as the universe expands. If you have a cubic meter of space today, it contains a certain amount of dark energy. Tomorrow, when the universe has expanded slightly, that same cubic meter of space still contains the same amount of dark energy, but now there are more cubic meters of space, each with their own dark energy. The implications for cosmic scale are staggering. Dark energy ensures that the universe will continue expanding forever and at an accelerating rate. The distances between galaxy clusters will grow exponentially over time. The cosmic scale we've been discussing throughout this journey is just the beginning. The universe will become vastly larger than it is today. But there's something even more mind-bending to consider. Some theories suggest that what we call dark matter and dark energy might be evidence of additional dimensions of space beyond the three we experience. We're familiar with 3 dimensions of space: length, width, and height, plus 1 dimension of time. But string theories and other advanced physics theories suggest there might be as many as 10 or 11 total dimensions. We can only perceive 3 of them directly because the others are compactified, curled up so small at every point in space that we can't detect them directly. This might be exactly our situation with space itself. We perceive 3 dimensions, but there might be additional dimensions curled up at every point in the 3-dimensional space we can perceive, too small for us to detect directly. These extra dimensions could be where dark matter and dark energy come from. If this is true, then the cosmic scale we've been exploring is just a 3-dimensional cross-section of a much higher dimensional reality. The universe isn't just larger than we can see, it exists in more dimensions than we can perceive. Think about what this means. We've been talking about galaxies separated by millions of light years, about an observable universe 93 billion light years across, about a possible infinite cosmos stretching in all directions. But this entire discussion has been limited to just 3 dimensions of space. If there are additional dimensions, then at every point in the three-dimensional space we can perceive, there might be entire universes worth of space curled up in the extra dimensions. The cosmic scale might be infinitely larger than anything we've discussed, not just in the three dimensions we know, but in additional dimensions we can't even imagine. This raises profound questions about the nature of reality itself. When you reach out your hand to touch a table, you think you're touching a solid surface. But from the perspective of extra dimensions, you might be reaching through vast spaces in those higher dimensions, and the solid table might be mostly empty space when viewed from the perspective of all dimensions. The atoms that make up your body, the earth, and everything around you might be extended structures in higher dimensions, like three-dimensional shadows cast by higher dimensional objects. Your entire existence might be taking place on what physicists call a brane, a three-dimensional membrane floating in a higher dimensional space. If this is true, then there might be other branes floating nearby in the higher dimensions, each containing its own universe with its own galaxies, stars, and planets. These parallel universes might be incredibly close to us in the extra dimensions, perhaps less than a millimeter away, but we can't reach them or detect them directly because we're confined to our three-dimensional brain. This possibility makes the multiverse concept we discussed earlier even more mind-boggling. Not only might there be multiple universes created by eternal inflation, but there might be multiple universes floating in extra dimensions, all of them potentially infinite in size within their own three-dimensional spaces. The cosmic scale we've been exploring throughout this journey might just be one layer of an infinitely layered reality. Your galaxy, vast as it is, might just be one galaxy in one universe on one brane in one small region of an infinite higher dimensional space containing infinite numbers of universes, each with their own infinite numbers of galaxies. But let me bring this back to something you can actually think about. Whether or not extra dimensions exist, whether or not dark matter and dark energy are evidence of higher dimensional physics, one thing is clear. The universe is far stranger and far larger than anything our ancestors could have imagined. We've discovered that most of reality is invisible to us. We've learned that space itself is dynamic, expanding and creating more of itself over time. We've found evidence that what we can perceive might be just a tiny fraction of what actually exists. This invisible universe, this vast realm of dark matter and dark energy, and possibly extra dimensions, doesn't diminish the importance of the visible universe we've been exploring. Instead, it amplifies it. The fact that galaxies and stars and planets and life can exist in such a strange, mostly invisible cosmos makes their existence even more.
The invisible universe, dark matter, dark energy, and hidden dimensions. Everything I've told you so far about cosmic scale has been a lie. Well, not exactly a lie, but a profound understatement of the true scope of reality. Because everything we've discussed, Are we alone? The search for consciousness across cosmic scales. In all our journey through cosmic scale, we've encountered one profound mystery that makes every other mystery pale by comparison: consciousness. In a universe containing trillions of galaxies, each with hundreds of billions of stars, each potentially hosting multiple planets, why have we only found consciousness in one place, here, on Earth? This question becomes even more puzzling when you consider the scales we've been exploring. If the observable universe contains roughly 10 to the 24 stars, and if even a tiny fraction of those stars have planets in the habitable zone, and if even a microscopic percentage of those planets develop life, and if even an infinitesimal fraction of those develop consciousness, the numbers still suggest there should be millions or billions of conscious civilizations in our observable universe alone. So where is everybody? This question, first posed by physicist Enrico Fermi in 1950, becomes more haunting the more you understand about cosmic scale. With so much space, so much time, so many opportunities for consciousness to emerge, the silence from the cosmos is deafening. But what if we're asking the wrong questions? What if consciousness across cosmic scales doesn't look anything like what we expect?
What if we're surrounded by forms of awareness so different from our own that we don't even recognize them as conscious? Let me take you on a journey through the possible forms consciousness might take across the scales we've been exploring, from the quantum realm to cosmic superclusters, and show you why the search for consciousness in the universe might require us to completely reimagine what consciousness actually is. Let's start with what we know about consciousness on Earth. Human consciousness emerges from the complex interactions of about 86 billion neurons in your brain. Each neuron is connected to thousands of others, creating a network of staggering complexity. The total number of connections in your brain is larger than the number of stars in our galaxy. But human consciousness is just one type of consciousness on Earth. Octopuses have evolved consciousness independently with a completely different neural architecture. Their nervous system is distributed throughout their body, with most of their neurons actually located in their arms rather than their brain. They can solve complex problems, use tools, and even seem to have personalities, but their consciousness is probably utterly alien to ours. Dolphins and whales have complex social behaviors and sophisticated communication systems. Some scientists believe they might have forms of consciousness that are actually superior to human consciousness in certain ways, particularly in terms of emotional intelligence and social awareness. Even more alien are the forms of collective consciousness we see in social insects. A single ant is not particularly intelligent, but an ant colony displays behaviors that seem to indicate a form of collective intelligence. The colony can solve complex problems, adapt to changing circumstances, and make decisions that benefit the whole. Is the colony itself conscious in some way that we don't understand? Now, let's scale this up to cosmic dimensions and ask, what forms might consciousness take across the vast scales of the universe? At the planetary scale, some scientists have proposed that Earth itself might be conscious in a way that we don't recognize. The Gaia hypothesis suggests that the Earth's biosphere, atmosphere, and geology form an integrated system that maintains conditions suitable for life. Could this global system have some form of awareness? The Earth processes information on a massive scale. Every day, billions of living organisms respond to environmental changes, chemical cycles move elements around the globe, and weather patterns distribute energy across the planet. The total information processing capacity of Earth's biosphere might be far greater than the information processing capacity of any individual brain. Could consciousness emerge at this planetary scale? Could Earth be aware of itself and its place in the solar system in ways that we can't perceive because we're embedded within it, like individual neurons that can't perceive the consciousness of the brain they're part of? This idea becomes even more intriguing when we consider that there might be billions of planets in our galaxy alone. If planetary consciousness is possible, then our galaxy contains billions of conscious worlds, each with their own unique form of planetary awareness. But let's go even larger. What about solar systems consciousness? Our solar system is a complex dynamic entity with intricate gravitational relationships, magnetic field interactions, and flows of matter and energy. The Sun's magnetic field extends far beyond the planets, creating a vast sphere of influence called the heliosphere. Could this entire system have some form of integrated awareness? If solar system consciousness is possible, then our galaxy contains hundreds of billions of conscious solar systems. The Milky Way would be not just a collection of stars and planets, but a vast community of solar system minds, each with their own unique perspective on cosmic reality. And what about galactic consciousness? Our galaxy is an incredibly complex system with spiral arms that maintain their structure over hundreds of millions of years, with flows of gas and dust that feed star formation, with a supermassive black hole at the center that influences the dynamics of the entire system. Could our galaxy be conscious? Could the complex interactions between hundreds of billions of stars, the flows of matter and energy, the magnetic fields that thread through the galactic disk, could all of this constitute a form of awareness that operates on timescales of millions or billions of years? If galactic consciousness is possible, then the observable universe contains trillions of conscious galaxies. The cosmic web we discussed earlier wouldn't just be a network of gravitationally bound structures, it would be a vast neural network of galactic minds with information and perhaps consciousness flowing along the filaments that connect galaxy clusters. This brings us to the ultimate question: can the universe itself be conscious? The universe processes information on an unimaginable scale. Every particle interaction, every gravitational wave, every quantum fluctuation represents information being processed. The total information processing capacity of the universe might be infinite. Moreover, the universe seems to have emergent properties that aren't present in its individual components. Galaxies, stars, and planets emerged from simpler components through complex interactions governed by physical laws. Consciousness emerged from simpler biological components through evolution and neural complexity. Could universal consciousness emerge from the complex interactions of all the matter and energy in the cosmos? If the universe is conscious, then every atom in your body, every thought in your mind, every galaxy we can observe is part of a cosmic mind.
Are we alone? The search for consciousness across cosmic scales. In all our journey through cosmic scale, we've encountered one profound mystery that makes every other mystery pale by comparison: consciousness. In a universe containing trillions of galaxies, each with hundreds of billions of stars, each potentially hosting multiple planets, why have we only found consciousness in one place, here, on Earth? This question becomes even more puzzling when you consider the scales we've been exploring. If the observable universe contains roughly 10 to the 24 stars, and if even a tiny fraction of those stars have planets in the habitable zone, and if even a microscopic percentage of those planets develop life, and if even an infinitesimal fraction of those develop consciousness, the numbers still suggest there should be millions or billions of conscious civilizations in our observable universe alone. So where is everybody? This question, first posed by physicist Enrico Fermi in 1950, becomes more haunting the more you understand about cosmic scale. With so much space, so much time, so many opportunities for consciousness to emerge, the silence from the cosmos is deafening. But what if we're asking the wrong questions? What if consciousness across cosmic scales doesn't look anything like what we expect? What if we're surrounded by forms of awareness so different from our own that we don't even recognize them as conscious? Let me take you on a journey through the possible forms consciousness might take across the scales we've been exploring, from the quantum realm to cosmic superclusters, and show you why the search for consciousness in the universe might require us to completely reimagine what consciousness actually is. Let's start with what we know about consciousness on Earth. Human consciousness emerges from the complex interactions of about 86 billion neurons in your brain. Each neuron is connected to thousands of others, creating a network of staggering complexity. The total number of connections in your brain is larger than the number of stars in our galaxy. But human consciousness is just one type of consciousness on Earth. Octopuses have evolved consciousness independently with a completely different neural architecture. Their nervous system is distributed throughout their body, with most of their neurons actually located in their arms rather than their brain. They can solve complex problems, use tools, and even seem to have personalities, but their consciousness is probably utterly alien to ours. Dolphins and whales have complex social behaviors and sophisticated communication systems. Some scientists believe they might have forms of consciousness that are actually superior to human consciousness in certain ways, particularly in terms of emotional intelligence and social awareness. Even more alien are the forms of collective consciousness we see in social insects. A single ant is not particularly intelligent, but an ant colony displays behaviors that seem to indicate a form of collective intelligence. The colony can solve complex problems, adapt to changing circumstances,